So if anyone's interested in this, that paper is out. It's open access too, so I don't need a subscription for it. But we looked at Hurricane Ana and Arthur. Ana gave about 300 millimeters of rain to Oahu in the Big Island. Even though it didn't make landfall, it went to the south of us. Arthur made landfall on North Carolina, but brought about 200 millimeters of rain. And what we did was do a series of simulations where we had a very high resolution, 2/3 of a kilometer using WRF, short-term simulations, 12 or 18 hours, and we tested a bunch of different microphysics schemes to see if they could reproduce the polarimetric signatures that we see with the radar. And so each of these schemes is either single moment or double moment in different things, different cloud species. And we used a simulator to essentially calculate the radar backscatter that you would get from the model to compare with the observations. And this simulator is, by the way, on my GitHub page. It's open source, so if anybody wants to use it, you're welcome to. Welcome to contribute to the code. And so this is what the actual radar data looked like from ANA. So radar reflectivity on the left. You can see it was a sheared system with all the convection on the down shear side. There's Oahu. We were getting lots and lots of rain. Look at you may be familiar with this, but the differential reflectivity, hard to read these numbers. This is 3 here, 3 dB. This is 0. So you notice that almost all the radar, the differential reflectivity is sort of between about 0.5 and 1.5 as the numbers that we were getting from that. If you look at the simulation in terms of the intensity, it's a lot of variation depending on just changing the microphysics. This is the best track, and this is the spread. This is in knots, so ranging from 130 knots to 70 knots in a 9-hour forecast. Very sensitive to the microphysics here. The blue line is the best one. That's a spectral bin model. That's extremely advanced microphysics. And but if you look at what the model showed, the reflectivity looks pretty good. This is the real data here. This is Thomson double moment scheme, and this is the spectral bin. Interestingly, the Thomson actually looks kind of the best. I'm only showing you the two best ones. Thomson looks pretty good. Spectral bin is okay, but it doesn't get the peaks. You notice it's washed out. The structure is not quite as good. I think this might be resolution still. We still need higher resolution model to get that. The ZDR though is pretty bad. This is the real data. It's getting large sections of it right, but you see these big swaths of yellow, 3 and 3.5 dB that just are not in the real data at all. So we've been working with Greg Thompson to try and fix this, and we think we might have a solution. But we're going to try and present that at the AGU in December. So stay tuned there. If you look at a statistical distribution, so this is a PDF of ZDR and Z here. This is so the yellow color here is the peak frequency of radar echoes. The black is the 50% contour. So you can see the radar composite is sort of maximized around 1 dB and about 35 dBz. But look how bad some of the microphysics are. This is the single moment. It cannot represent the breadth of the distribution at all. The only way it can make more rain is by making the drops bigger, right? Because it has only 1 degree of freedom. As you go to the double moment schemes, it gets better, but like Morrison is too high here. Thomson is sort of the best. It has it kind of right. It's a little bit low, but it has that region of very high ZDR here that is not found in the observations at all. And that's what we were working on to try and get rid of. The spectral bin actually gets the mode just about right. It's a little low, but it doesn't get the extreme values. It's not able to represent the highest rainfall. And so then the last thing I want to show is if you actually relate this back to rainfall, the accumulated rainfall from these schemes is so strongly dependent on the microphysics. You'll see that these are the single moment schemes at the top here for Arthur and Ana. As you increase the complexity of the scheme, you see that the rainfall rate goes down. That the single moment schemes are really overproducing the rain to a large degree. And what we found that was quite interesting is if you actually link those two together, take the peak accumulated rainfall from each scheme and plot it against the intensity bias, we get actually a very strong correlation. This is about 0.95 correlation that the schemes that are overproducing the rainfall are also overproducing the intensity. So it goes back to these same ideas about heating, where the heating is in the eyeball, also related to the rainfall rates. So I wanted to show this to kind of wrap it up with the very beginning of my talk. Track intensity and rainfall. If we can't, to solve all of these problems, we have to solve every problem. We can't tackle just one thing. I think we have to fix rainfall to fix intensity, and that will also help us with the track. So, but before you go out and, the Thomson and spectral bin are the best ones, but keep in mind that the spectral bin costs about 1,500% more computational time than the single moment scheme. So we may know a lot about the physics, but we have more computing power that we need to do some of that stuff. Okay, so I'm going to skip. Sure, yeah.
In your simulation compared with the radar observation, the radar observation is ground-based one, like not confirmed.
Yes.
Radar.
Yes. This is all ground-based radar. Yes.
Not airborne.
Right, and that's part of the. But yeah, I wanted to motivate. So if we can get polarimetric data in for the airborne, we'll be able to do some really amazing things. Like this is just rain too. We didn't look at ice yet. So I think the ice has also got problems. But so we have a manuscript. We're looking at the ice now too. Evan Kalina from NOAA is looking at the ice. Okay, so I want to finish. Okay, ahead. Yeah.
Do you have so you only use the polarimetric parameter for the ZH and ZDR. How about the use of rho HV and KDP? Do you?
Yes, we used rho HV to as a quality control, just to make sure we were only looking at raindrops. We didn't use KDP in this case, but we're looking at that now, especially with the ice, to look at high concentrations of ice crystals. Yes.
Thank you very much.
Yes. Sure.
Could you explain how to calculate the ZDR for simulation?
Oh, sure. Yeah, so go back. Let's see here. So I use the T-matrix scattering method, and we basically calculate the drop size, and then we do a scattering calculation for the drops. And from the model, we have the full drop size distribution, so we can simulate exactly what the radar volume would be. So, but we didn't. We did a very idealized radar with no problems of real radar.
So using just the QR,
yeah, we use QR and NNT. Yep. Except for the spectral bin, where we have it's got 33 bin sizes. We calculate for each bin independently. Yeah. So that's another issue with the SBM is the amount of output is much higher than the single moment or double moment. Okay. So even with 3 hours, I keep going. I'm going over. So, but I did want to just. Yeah. Oh yes. Question.
And then your model simulation is a walk with the different microphysics schemes. So you use WDM6 schemes, right?
Mm-hmm.
So in your model simulation, how could you set up the initials, PCN concentrations?
Yes. We used a tropical, so 100 per cubic centimeter for the initial CCN concentration.
Using observation.
Yeah, well, I mean, it's not so much observed as just assumed. Yes, so I will say that the Thomson aerosol aware, one thing we noticed, we used the original Thomson from 2008, and then also the Thomson aerosol aware that has some prognostic CCN, and the new one is much better. It produces smaller drops than the old Thomson. So I think that has a lot to do with why the Thomson was one of the best schemes. So yeah, we could play around with more of the parameters, but we wanted a sort of proof of concept for this. So yeah, good question. So okay, I'm just going to skip through and end so we can have a little more discussion before lunch, or save the discussion for after lunch. I already showed these before. We have a new project called LROSE. So one of the challenges with airborne radar is it's actually quite difficult to use. Many people do not use the airborne radar. So we're going to try and make some better software tools. But certainly if anyone is interested in using airborne radar data from these previous projects, let me know. I'd be happy to help. Or come visit Colorado and come work with me and my students for a while. That's a good way to do it. But we're going to have this project is just getting started. In fact, I got the email today that the money was awarded. So we'll start work in a couple of weeks. And then the future field experiments, we talked about this mostly on Wednesday, so I won't go into it again, but I would like to work with you for YMC. Since this will correspond with your observation period for T-Part 2, and maybe we can get some coordinated effort to fly, if you could fly a storm that we're also interested in, that would be great. So we'd definitely like to stay in touch for that. As well. And then I would definitely like to keep in touch about a new potential project in maybe 2020 timeframe, maybe 2019. We're going to talk about that more later this year, so I will keep you informed. And I think that heavy rainfall is still one of the major problems. And so if we could work together, if I can get a NOAA P3 to the Pacific, that's my goal. To come and have more aircraft, intercore aircraft penetrations. Or a C-130, but I really want a P3 with the airborne Doppler radar. So that's my goal. So, I've already said all this. Aircraft observations have greatly advanced our knowledge of TC structure and intensity change. I've been fortunate to be a part of many good projects, RAINX, TPARC, PREDICT, and TCI. We still have a lot of work to do though. So new technologies, new dropsondes. I know you guys are working on your dropsonde system, so I think there's still a lot to be done there. Phased array, polarimetric radar is a real new frontier for the future of tropical cyclone studies. We've had very limited data because we've had to have the storms come to us, but hopefully we can get the aircraft to bring the radar to the storm. New software tools, and then as I mentioned, I think the work that you're doing here is going to be really valuable, and I look forward to it, and I wish you much success, and I hope I can help contribute. So with that, I'll say arigatou gozaimasu.
Any questions?
Please show cross-section of temperature anomaly.
Oh, yes. There we go. Yes.
I look like it. Air of stratosphere descends and form air of stratosphere compose warm core and this outward this stratosphere, air of stratosphere descend and
Yes.
warm this and this air move outward to outflow area. But for example, Soria-Gay-Lassen equation is Saturnary circulation of Soria-Gay-Lassen equation is
Yes.
secondary circulation rate. So why
Good question. Well, I would say a couple of things. One is these analyses are still somewhat preliminary, so some of the details may change as we finalize the analyses. So I would not take too much. It may change. But I think that this gyre we're seeing here is consistent with Sawyer-Eliason upper level heating. You'll notice there are two warm core. There's this one and this one. And that's something that Stern and Zhang talk about. The specific structure of the warm core depends strongly on what reference state you use. So if you can actually make this one stronger or this one weaker, depending on that reference state. I think in this case, one of the big reasons why we see this type of structure here may be largely due to the center, because the storm is starting to become tilted. So whenever we do an axisymmetric analyses, we have to be very careful where we put the center. If you move it a little bit, you might get a slightly different radial wind structure as well. So I like the idea here that this air is coming in and picking up some of this moist or warmer air, and so maybe some eye-eyeball mixing is occurring here. That may be part of the reason. So it's an inertial overshoot from what the Sawyer-Eliason would show. So going back to ideas about supergradient winds. But this is pretty high in the atmosphere, so I don't know if that's the case or not yet. So it certainly seems consistent, but I will keep working on the analysis, make it better.
Could you tell me what the size of a typical warm core?
I think it varies significantly, yeah.
And if you make analysis, variation method, I believe the warm core should be inside eyeball, but some satellite analysis shows a more wider area of the positive anomaly, temperature anomaly. So I can't understand how to identify where is the outer boundary of warm core.
I think a lot of that has to do with the limitations of the satellite. Like the AMSU satellite has a very large footprint, and so I think the spatial resolution is
satellites tend to overestimate the size of a warm core.
I think so. There was a paper recently, it might be by Fuqing Zhang, I'm not sure, but they looked at that. We're trying to compare the two. Some people are doing some stuff with GPS occultation now to try and get better estimates of the warm core, but then you also have problems with spatial resolution. So we need more observations like this, direct dropsons in the middle. But you can see, I mean, here, this is all positive. So I don't know where you draw the line for the warm core. It's all, it depends a lot in this case, though, on that specific reference state. So yeah, that's something. Several other researchers for TCI are very interested in that comparison of satellites with the dropsons to do warm core. So I expect some studies to come from this work.
I think Hioki-san says, that in this case, a little bit, different from the typical cases. For example, like maximum tangential wind is seen about 5 kilometer height, right? Mm-hmm. So, and it is related to, seems to me, related to the middle level inflow over here, and coming inside, so it gives a large, tangential velocity over here, right? Yes. So maybe it is related to the strong warm core in a lower warm core, might be. Maybe it gives some, this kind of shape of, the contours of equivalent potential temperature. So it should follow, if the analysis is right, maybe this figure gives very interesting, features.
Yeah, I agree.
It shows.
Yeah, that's a good point about this, the intercore warm core. I think part of the challenge, because I also have concerns about this, being that high, and that's why I mentioned. Go back to this one here. The center, in this case in particular, makes such a huge difference because it's such a small storm. I mean, you see this 80 meter per second maximum here, and this broad 70 meter per second maximum here. So if I move the center just a little bit, this will get lower in the axis symmetric.
Right.
But if I put it, here versus there, so I need to play around with that a little bit more, and maybe use an average. My student's been looking at that. So
Or some kind of mixture, during, inside of the eye wall and the center regions. Maybe that some kind of horizontal uniformity of values maybe
Yes.
indicate that.
So we want to tighten up the analysis a little bit more. So, but yeah, I mean, I don't think it's wrong what I've shown. If I did, I wouldn't show it. But I don't want to say I would, that it's 100% right yet.
At least it's very interesting.
Yes,
thing.
exactly.
Yeah.
Could you show me the same figure for the cut when the cut was cut from cut 3?
Yeah.
This time it also has a dual one.
Yes, dual. Yeah, but the lower one is weaker, but it does have a dual one.
Is it the yellow or
Yeah, I think in the model we frequently see the dual one core. So in fact, yeah, Dan Stern's paper is all about the dual one core. So I think it's real. Yeah, and actually that's the thing that the thermodynamics are not as sensitive to the dropson or to the center. The radial wind and tangential wind, if you change the center, you will change the projection. But and the vertical motion will change too. But the thermodynamics are a scalar, so it's less sensitive to that. So I feel pretty confident, certainly in the vertical, whether it moves radially a little bit, but I feel pretty confident in that dual one core. And you do see, just like what you just talked about, this air coming in here, coming from that lower one core, may be very important.
It seems to me, indicates some mixture or like a entrainment or something like that. Yeah, possible.
Okay. Understand.
Yes.
Thank you very much. New questions?
Oh, sure. Yeah. Okay.
For the cloud radar, double band radar, so maybe you scan into the particular, maybe the forward direction RHI for the, not RHI, maybe the from the downward pointing to the vertical point, upward pointing. So maybe you can get not only the cumulus, but also the cirrus clouds.
Yes.
So do you have any plan to get on loaded on the cloud particle counting or probe for the particle or the cloud application the particles obtained for the size and shape and number concentration in the
Yes.
G5. Simultaneous loading on the insights of observation instrument and also the double band radar.
Yes, and that was a big part of what they want to do with that radar.
Yeah.
So, but they won't do that in a hurricane probably, in a tropical cyclone. Well, you can get the upper level, like very high level cirrus, and things. So yes, but a big problem with so for the cloud radar, for the C-130, it has lots of cloud particle instrumentation as well. The big challenge is that nobody wants to fly in the very interesting region around -10°C because of aircraft icing concerns. So that's where the cloud radar, either the cloud radar or the polarimetric C-band radar will have to be important because we can't fly. We can't make direct measurements in the mixed phase.
But you said that the hyper cloud radar is already on the G5?
Yes.
No?
Yes.
It's the G5 that you can get on the high level cirrus cloud.
Yes, you could definitely get that. And we did in PREDICT, actually. There hasn't been very many papers about the ice crystals in PREDICT, but there are a few. So mostly we're looking at dropsons and dynamics, but there were some cloud measurements in PREDICT that we have. So actually some direct measurements of the Saharan air, too, the aerosols in the Saharan air layer were made during the day. So, yeah.
Thank you very much.
Okay, thank you very much for your informative presentation. And it's sometimes difficult for Japanese to follow English presentation, but I know you have spoken slowly enough for us to follow your presentation. And we know that preparing 2-3 hours presentation material is not an easy task. So we truly appreciate your time and effort in preparing this presentation and giving us this wonderful presentation.
Thank you. Well, please do email me. I know that you may have questions that, especially in English, may take you longer to formulate. So feel free to take your time and write them in email, and I'd be happy to answer them over email as well. Or send them for translation. I can't answer in Japanese, but I'd be happy to answer in the rest of the day too.
So let's give big hands to Professor Michael Bell. What time will we start the afternoon session?
So maybe I think this is as scheduled. I estimated you are running out of your time. So I think we can take 1 hour lunchtime, right? And we can resume 1:45, and 1:45 we start from the Canada-san's talk. Is that okay?
Yes.
Okay. Okay. Thank you very much again.
Thank you.